want to tell you something about these polyatomic ion sheets, okay? And please don't shoot the messenger. Okay? Technically speaking, you are responsible for everything on here. However, okay, there are some that you are going to see more often than not, okay? And I will tell you what those are. Most of those are ones that you probably remembered from last year. So, let me tell you what those are. If you want to highlight them or put a little star next to it, whatever. Here we go. Ready? In the first column, you need to know acetate, all of the chlors, hypochlorite, chlorite, chlorate, perchlorate. Skip one, I would know bicarbonate. Skip another one, nitrite, nitrate, and hydroxide. And let's call it, that's about it for the first column. Second column, you should know carbonate. Skip one, chromate, dichromate, sulfite, and sulfate. And that's it for the middle column. And in the third column, I would know phosphite, phosphate, and ammonium. So, my recommendation, ladies and gentlemen, I would make flashcards for all of them. However, when you're studying, if you find yourself in a time crunch, you might just want to go over the ones that we've talked about. Okay? Those are the ones you will see most often. Okay? All right, so check your answers. Here we go. One thing somebody asked me last class, with a word like decoxide or tetroxide, if you put deca oxide or tetraoxide, that's fine, okay? I wouldn't count off of that, nor would the AP graders. Technically speaking, if you have two vowels running up against each other like that, the A and the O from oxide, you just take the A off, but it won't be marked wrong if you don't do that. Okay? Remember that, and again, I suggested to you, anytime you're asked to do this sort of thing, go through and decide, is it ionic or is it covalent? Remember your covalents, those are the easy ones. The prefixes become your subscripts. If something is ionic, however, you need to think about charges. Okay? You only have to think about charges when you're doing ionic, not covalent. So any that you want me to talk out or anything, you feel pretty comfortable with it?
2 thumbs up.
All right. Okay. Let's finish this up. And the last thing we have to talk about, acids. Okay? Now, first of all, what defines an acid? Ladies and gentlemen, an acid is defined as something that when you dissolve it in water, produces hydrogen ions. Okay, so it has to produce hydrogen ions. That means it must have hydrogen in its formula. And let's even be more specific. Okay, how do you recognize an acid? An acid will always begin with hydrogen. If you look on our previous 2 slides, you will notice that nothing there had hydrogen as the first element. Okay? And guys, we have 2 types of acids. Oxyacids and what I call binary acids. An oxyacid is exactly what it sounds like. It's an acid that has oxygen in it. And for our purposes in here, that is pretty much going to always mean hydrogen joined to one of our polyatomic ions. A binary acid, however, still an acid, so it has to have hydrogen. It's hydrogen joined to one other thing, one other element. Right? And they each have a slightly different naming system. To name or write your formulas for your oxyacids, ladies and gentlemen, you need to know your polyatomic ions backwards and forwards. Okay? If you don't know the names, formulas, charges of your polyatomic ions, it makes dealing with oxyacids very, very difficult. If you see an acid, remind me, how do you recognize an acid if I just give you a formula? How do you know? Begins with hydrogen, and you see that oxygen is in the formula as well. Then you say, okay, that's an oxyacid. And you need to ask yourself, what is the name of that polyatomic ion it is joined to? If the name of that polyatomic ion ends in -ate, like nitrate, it becomes nitric acid. If the polyatomic ion ends in -ite, like phosphite, it changes to an -us ending. It would be phosphorus acid. And years ago, my students came up with this little way to remember it. It's really stupid, but it'll help you remember it. If you ate something gross, it makes you feel ick. If you get in a fight, you need us. Okay, it's dumb. I know. I know. It's dumb. But at least it helps you remember. Ate goes to ick. Ite goes to us. And there's just a few ones that you have to kind of watch out for. For example, sulfate does not become sulfic acid. It's sulfuric. And it's not sulfus. It's sulfurous. Similar situation with the phosphates. Phosphate does not become phosphic. What would it be? Phosphoric. So let's just do some examples together real quick. Look at all three examples. They are all acids. They all start with H. They are all oxyacids because they all have oxygen in them. Think about the names of these polyatomics. What is the name of that polyatomic ion? Chromate. So, what is it? Not hydro, just chromic. Shush, please. What is the name of that polyatomic ion? Perchlorate. So, perchloric.
Hold it.
Alright, how about this last one? What is the name of NO2? Nitrite. So, nitrous. Nitrous acid. Alright, let's talk binary acids. Ladies and gentlemen, how do you recognize a binary acid? Still has hydrogen, but does not have oxygen. And if you will notice, ladies and gentlemen, on the previous slide, nowhere did we say hydro as a prefix. That is reserved only for binary acids. And the thing that is nice about binary acids, they always get that ick ending. Never, ever, ever do they get an us ending. Okay, so let's just do these together real quick. How would you name this first one? Hydrochloric. How about the next one? Don't worry about that number 2 that's there. How would you name it? Hydro what? Sulfuric. This one is a little bit tricky. This is considered a binary acid because it doesn't have oxygen. But that is one of our polyatomic ions. But folks, it's still a binary acid, so it still follows these rules. How do you think you're going to name this one? Hydrocyanic. It's a weird sounding word, I know. Hydrocyanic. Okay. Folks, you need to be able to go the other way. Words, names, to formula. I'm going to do one of them with you. Let's do this third bullet. Let's do carbonic acid. Okay, you come across these two words and you are asked to write the formula. First thing I would think in my brain is, okay, the word acid is there. What is the first element then? Hydrogen. Tell me what hydrogen's charge is always. +1. Now folks, look at the first word. Please notice that you do not see the prefix hydro. That means something, that should mean something to you. Look at the ending, that should mean something to you. This is hydrogen joined to what? Carbonate. And what is carbonate's charge? -2. The two charges here do not add up to equal 0, so I've got to do what I call the swap and drop method. So, what is the formula? You got it. Try the rest of these on your own, please. Go. So, folks, this is the chapter that has some of the heavy-duty math, okay? It's not to say that, you know, there won't be math for basically the rest of the year, but a lot of the introductory math is in this chapter, most of which you will have done before. There are some more challenging problems that you may not have seen before. Okay, so let's just start with some basics. First of all, people use the word stoichiometry incorrectly very often. A lot of people think that anytime you're doing some kind of conversion, anytime you're using a T-chart or dimensional analysis, that is stoichiometry. Not correct. Stoichiometry is doing conversions along with a chemical reaction. If you don't have a chemical reaction going on, it's not stoichiometry. It's just doing a conversion. Okay? So, we're not going to get into this today, but, you know, if I give you 36 grams of a reactant, and I say how much product will be produced, that is a true stoichiometry problem. Alright, now I want you to look at your periodic table, which hopefully is out. Within the box for every element, you've got your atomic number, which is the big number, but you have the number with all the decimals. That is your atomic mass. And ladies and gentlemen, that is the mass of one atom of that element. Okay? It's expressed in units of atomic mass units, AMUs. One AMU is defined as a 1/12 the mass of a carbon-12 atom. Okay? We, however, are not going to be dealing with units of AMUs very often, and I'll get to that in a minute of what we will be dealing with. But first, I want you to understand why those numbers on your periodic table, those atomic masses, why they are not whole numbers. Why do they have all those decimals? The reason is, the definition of an atomic mass is the average of all naturally occurring isotopes. So let's just back up for a second. Do you remember the term isotope? It's two atoms of the same element, which means, what do they have in common?
Protons.
Same number of protons. They're the same element. They have to have the same number of protons. How do they differ? The number of neutrons. For example, I'm using copper here. If you see this notation where you have the element symbol and then there's a number sort of up and to the left, that is its mass number. Tell me, review from last class. What is the mass number? Number of what, Alex? Protons plus neutrons. So this is showing you these two isotopes have a difference of 2 neutrons. And if we went out into nature and gathered up every single carbon atom on Earth, which is not possible, but just go with me on it, 69.09% of them would be the carbon-63 isotope, and 30.91% would be the carbon-65. Now, true, you cannot go out in nature and scoop up every atom of that element. What they end up doing is just taking large enough sample sizes, and they continue to find these same percentages over and over and over and over again. So, if you'll notice, this is the actual atomic mass of copper. Please tell me, why is that average, all the ones on Earth, why is that number closer to 63 than to 65? Yeah, there's a higher percentage of 63. Okay? So it's going to be closer to it. Here's the thing. we are not going to deal in units of atomic mass units. We're not going to deal with AMUs. Because very rarely, if ever, are you going to be doing calculations involving one atom of something. Most of the time you're going to be dealing with lots of atoms, moles of atoms. Okay? And I assume you remember that number. It is called Avogadro's number. So, to make this clear, and I want to make sure you understand the difference between molar mass and atomic mass. Okay? And I'll use magnesium as an example. One atom of magnesium, just one atom, has a mass of 24.3 AMUs. One little teeny tiny atom. However, if I don't just have one atom, I have a mole of them, 6.02 times 10 to the 23rd, and I put that on a balance, on a scale, the scale will read 24.3 grams. And since we are very rarely going to be dealing with calculations where we are only looking at one atom, this is what we will be using. I'm never going to say what's the atomic mass of blah blah blah. I will say what is the molar mass, which is in units of grams per mole. Now find nitrogen on your periodic table. Put your finger on it. Why is this not 14? There's 2 of them. You have to account for all of your subscripts. Okay? I'm sure most of you remember that. I just wanted to refresh your memory. Okay, and our first little bit of calculation today. There will be times when you will be asked to calculate a percent by mass of something. Folks, any percentage, when you learned percentage way back in I don't even know what grade, 3rd grade maybe, percentages are always just part divided by whole times 100. And in this example, the percent of iron within this compound, part divided by whole. Now look at your periodic table and find iron. What is the molar mass of iron? 55 point... Okay, well how come that's not what this says? There's 2 of them. Okay? There's 2 of them within the mass of the whole thing. Okay? And by the way, I know on my slide I have gone to 2 decimal places. That's actually more than you need to. Anytime you're pulling a molar mass off your periodic table, it is okay to round to 1 decimal place. Same with percentages. Round your percentages to 1 decimal place. So, really quick, you might even be able to do this without a calculator. I want you to tell me what percent of CH4 is made up of hydrogen. So, please don't pull out your calculators for this one. What is the percent of carbon? 75%. Okay. If you had 3 elements, then that would become a little bit more complicated, but for the moment we're only dealing with 2. Alright, let's talk empirical molecular. Alright, I'm going to start with empirical. An empirical formula, folks, is a compound whose subscripts have been reduced down as much as they can. For example, do you agree if I had something like that? Do you agree that 2 and 3, you can't reduce that anymore?
Yes.
Okay. All right. Well, there's empirical, molecular, okay? Very often we'll have subscripts that can be reduced down. And I will tell you that a molecular formula is very often how that compound truly exists in nature. For example, this molecule, one of my favorites, is a very cool molecule. I'm not drawing it very well, but anybody know the name of this one? Somebody said it. Benzene. This is a very smelly compound. Okay? I just like it because its structure is cool. It's a 6-carbon ring. Okay? Now, if this is how the compound exists in nature, you might be thinking, well, then what's the point of ever dealing with an empirical formula? If this is how it really is, what's the point? Well, empirical formulas will make your calculations a little bit easier, and then you can deal with the more complicated molecular. Okay? So, to do an empirical formula problem, guys, there are basically 4 steps. And instead of talking through these 4 steps, I'd rather jump straight to an example problem. So, we're going to do this problem together just to review this process. Alright, the problem says, one of the most commonly used white pigments in paints is a compound of titanium and oxygen that contains 59.9% titanium by mass. Determine the empirical formula. First things first. This is a compound that only contains 2 elements. If 59.9% of it is titanium, what is the remaining percentage made up of? Oxygen. And what is that percentage? Okay? 40.1% O, not O2, just O. Okay. When you are asked to do an empirical formula problem, you will most often be given percent by mass information. First step, number 1, take the percent signs off of those numbers and put grams instead for both of them. That's step 1. Step 2. For each one, you are going to do a very short 1-step conversion to turn each one from grams into moles. And let's just review a little bit. What number should I put on the top here?
1.
And where is the number on the bottom coming from? Your molar mass. And what is the molar mass of titanium? 47.9. Okay. Same thing down here. Oxygen's molar mass is? Very good. And we'll do the math. And by the way, it is in your best interest at this stage right here, where you get answers in moles, leave at least 3 decimal places. I'll explain later why that is a good idea. Alright, so step 1, we took the percent sign off, we changed it to grams. Second step, We converted each one into number of moles. Do you remember the third step? Divide by the smaller of the number. This is my smaller number. And I'm going to get a 1 here. This divided by that is 1. This is basically 2. Might not be exactly 2.0000, but it's 2. What are these numbers that I've circled? Subscripts. Do you agree that these subscripts cannot be reduced down any further? Say yes.
Yes.
All right.
Yeah.
Then that is my final answer. Now, folks, this was a very simple example. Sometimes when you do this division step here, you will get nice, pretty whole numbers. Sometimes you won't. What if I did this division here, and for the top one I got 1, but for the bottom number I didn't get 2, I got 2.5. Well, you can't have a 2.5 subscript, that's not going to work. Alex, tell me what to do.
Can you multiply them both by the same number for both whole numbers?
Okay, multiply both of these numbers by a whole number to get to a whole number. What do you suggest I do for this specific example?
Multiply by 2.
Sure, sounds good. So that would mean that my empirical formula would be this. Can 2 and 5 be reduced down anymore?
No.
Nope. Okay. Let me give you another scenario. What if you came up with 1 and 2.333? What are you going to do? You got to get it to a whole number. Alex.
Multiply by 3.
Sounds good? That would get you to a whole number. What if, here is your last possible scenario. Yes, I know it's an ominous number. What should I multiply by? Nope, not 5. Come on, math people.
3.
3 will work. 3 will get you to a whole number. So, guys, what I'm trying to show you here is, when you do this divide by the smallest number of moles, when you do that step, you're going to have a couple of possible scenarios. You're either going to automatically end up with whole numbers. That would be great. You might get a 0.5. You might get a 0.33. You might get a 0.66. Let's say you do this step and you get a 1 on the top and 2.83. If you get a number like that, that means one of two things have happened. Either you've put something into your calculator wrong and you've done a miscalculation, or the more likely cause for the error, this is the #1 most common error I see on these problems, is you rounded too much. That's why I say leave at least 3 decimal places. The more decimal places you leave, the easier it will be to see what this number is supposed to be. Okay? Because folks, think about, just as an example, think about if I had rounded this to 2.5, chop that off, and 1.3. That is not going to get me the correct answer here. So be careful. Don't round too much. talk molecular. Oh, okay. Now, sometimes you will have problems where they just ask you to find the empirical. Most of the time, however, guys, you will be asked to not only find empirical, but the molecular formula as well. And I have put this highlighted in yellow, super duper important. You cannot find a molecular formula. You can't do it unless the problem has given you the molar mass of that molecular formula. Okay? So, what I want you to do, this is an empirical and molecular problem. I actually want you to find the empirical formula on your own, and then stop. And we'll talk about the molecular part together. I just want to sort of introduce the problem a little bit to you. Very much like the last problem. This is a compound with only 2 elements in it. This is nitrogen and oxygen. Do not be thrown off by the fact that this problem does not have percentages in it. This has just straight number of grams. All that means is you can skip that first step. You don't have to take off a percent sign and put the grams on. They're already there. So I want you to solve for the empirical and then stop. Did you get that?
That's what I got. Yes.
Okay. Now, that would be the end of the problem if they had just asked for empirical, but they asked for molecular as well. Let me just scroll back up. Remember that you cannot do a molecular problem unless they give you the molar mass, which they have. Fine. Okay, great. Please tell me, what is the molar mass of 1 nitrogen and 2 oxygens? 46? Okay. 46 grams per mole. Does that match what the problem was telling us? No. The problem says it's 92. Folks, without even using a calculator, can you see the relationship between those 2 numbers? It's double. It won't always be double. It might be triple, it might be quadruple. But this is a doubling relationship, which means I need to double all my subscripts as well. And that is my molecular formula. Okay. This is the last thing we're going to do today. Listen up. There was a problem in your summer assignment almost identical to this one. And this is a problem that many people struggled with. Okay? I definitely did not get to this level in my Chem 1 class. Those of you that took honors, maybe. Okay? This is a challenging problem. So I'm going to go through it with you step by step. And I just want to tell you, this is a very important problem. Hint, hint. Okay?
Okay.
That's all I'm going to say.
Oh, is that what that means?
So here we go.
Just throw that.
The question says, a compound contains carbon, hydrogen, and oxygen. Folks, when you have a problem with not just 2 elements, but 3, you're introducing another level of complicatedness. I guess a better word would be complexity. Yeah. All right. It says combustion of a certain amount of the compound yields a certain amount of CO2 and a certain amount of water. What, just stop right there. What does that mean? Combustion of this compound. What does that mean?
Reaction with oxygen.
Okay. This compound, which I'm going to write out like this because we don't know what it is. This compound was reacted with oxygen, and we got two products. Can I balance that equation?
No.
No, because I don't know this formula. I don't even need to balance it, okay? I just wanted to show you what reaction we're looking at here. All right. Well, folks, let's deal with the empirical part of this first. And I want you to think about what you ultimately need to solve an empirical formula problem. You need the number of moles of each of the elements. We have 3 elements to deal with. We need moles of carbon, moles of hydrogen, and moles of oxygen to solve this problem. Okay, fine. I want you to read this second sentence and tell me, how am I going to find moles of just carbon? Where am I going to get that from? Correct. Okay? Folks, think about conservation of mass. Any carbon that I had over here is all going to be converted into carbon dioxide. If I know how much carbon dioxide I have, I can find moles of carbon. Now what I'm going to put up here, some of you will have done and some of you will not. Whether you have or haven't, I'm showing it to you now. I have a mass of CO2. And I need to get to moles of just C, not CO2. And this is how I'm going to do it. One step at a time. Where is this number coming from? Periodic table, what is the molar mass of CO2? Okay, 44. But I can't stop here. I don't want moles of CO2, I want moles of C, but I can get there like this. Okay? If you are ever in this situation and you're not sure about what numbers to put in here, wherever the whole compound is, that's always going to get a 1. Look at the formula for CO2. How many carbons are in CO2? Just 1. If I had been looking for moles of oxygen, up top this would have been a 2. Okay. Do the math. And I get that. Okay. Keep coming back. Keep reminding yourself, what do you need to solve this problem? You need moles of all the elements. Well, I've got moles of one of them. Let's go to the next one. Let's find moles of hydrogen. Where am I going to get it? From the water. Yeah. All of the hydrogen that was in this reactant is going to end up in the water. And we're going to do the exact same thing. You guys remember off the top of your head the molar mass of water? 18. Do the math. Alright. 2/3 of the way through. We've got moles of carbon, we've got moles of hydrogen. What's left? What do we need? Moles of oxygen. Well, let me scroll back up. And ladies and gentlemen, this is the challenging part. I want you to think about it and throw out some ideas. This is a challenging problem. Don't worry about being wrong. What do you think is one way I could find moles of oxygen? Alex?
Well, you take the number of moles of oxygen from the carbon dioxide and the water and add together, but then you're still going to have the moles of oxygen for the compound and oxygen.
Correct. Okay. I'm glad you said that, even though you realize there's a problem there. Okay? Many people would look at this problem and say, okay, well, we're going to do pretty much what we just have been doing. Figure out how many moles of O are in this one, how many moles of O are in this one, and add them together. I want you to understand why there's a problem with that. All of the oxygen that's on the product side, added together, includes some of this oxygen. And guys, I don't care about this oxygen. I care about how much oxygen is here. Okay? So, that method's not going to work. We know the mass of this entire compound. Let me scroll down. Can't I turn these both back into masses and subtract them from the total? Wouldn't that give me this? Okay. So, how do you turn moles of C into grams of C? Multiply by molar mass. Let's find out the mass of hydrogen. And folks, as soon as I write this out, some of you probably have already noticed, I really don't need to write out this calculation, but I will, just to be thorough, because the molar mass of hydrogen is just 1.0. Now what? Okay, put this together and make a total and subtract from what? This guy. Okay. Guys, I'm really trying to model here for you a process to get through these really long multi-step problems. You need to keep reminding yourself at every step, where am I trying to ultimately end up? Moles of each element. I've got moles of C, I've got moles of H. Can I get to moles of O?
Yes.
Yes. We're almost done. So, we've gotten through the hard part. What do you do now? You have moles of each of your three elements. What do? Divide by the smallest. Carbon and oxygen end up actually being the same number. Which means they're going to have the same subscript. So I get 1, and guys, I don't want you to just copy what I'm doing. I want you to see this in your calculator. These two right here. You don't get a 1. You don't get a nice pretty number. What do you get? 1.33. And this one is 1. How do you fix that problem? Multiply all three numbers by the number 3, and this is what you get. Just list them in the order they were given. Can those subscripts be reduced any further? Nope. That is our empirical formula.
We still need to find the
Yes, we do. We are going to have to find molecular, so listen, before I scroll up, tell me what is the molar mass of 3 carbons, 4 hydrogens, and 3 oxygens? 88. Does that match the molar mass given in the problem?
No.
No. This was the molar mass in the problem. Can you see the relationship? It's always going to be a whole number. Is it doubled? Is it tripled? It's doubled. And that is our molecular formula.